So we have established that the set L is open. Or have we? Wait, there's actually one or two things that we did not take account of that we have to actually check out. So first, notice that the x bar that I chose was closer to the indifference curve, the level curve of u, than to the axis. Suppose instead that, let's say I had chosen an x bar that was down here. Then when I drew this epsilon square, it would include, let's put it down there, there we go, okay. So that epsilon square now includes things that are not in R2 plus, and therefore they're not in L. So actually, it looks like the ball around x bar of radius epsilon, radius in the sense of the square, of radius epsilon, is actually not necessarily completely a subset of L. So maybe we didn't prove that L is open after all. But of course you can see that's easily fixed, because we could now say, okay, instead of taking this as epsilon, let's call this epsilon prime, and then let's call this distance here epsilon 2, that's how high it is, and the distance across here, call that epsilon 1, and then take our epsilon to be the minimum of this and this and this, so we would have a square that looks like this in that case, and lies entirely, actually the edge down here would be right on the axis, but it's less than epsilon that we're interested in. So everything is fine after all. We just have to do a little fast footwork here to show that we can make the things work, even if the point is not up here close to the indifference curve. So that looks like that's going to work, but there's still a problem. This is fine so long as the point is actually in R2 plus plus. It's in the interior of the quadrant. But what if it's on one of the axes? So let's suppose that the point is on this axis here. And so I'm actually going to get an awfully big square here, which was not what I wanted to do, but let's do it anyway. So the square is going to look very large when I do this little trick. And so now I can't do what I did over here, where I said, let's take the minimum of these different epsilons, because there is, no matter how small, and now let me use a different color here, no matter how small I make the square around this point, which is now our x bar. So let me just take this stuff off, because we're not going to be using this anymore anyway. So let's take this off, if I can get it off, and let's point out that this is now our x bar. And there is no epsilon ball or square about x bar that is entirely in L, because there's always going to be this part that's sticking out, like what we had down here a little while ago. There's always going to be this part that's sticking out over here. And so let's see about that. We're going to take this off now. So let's, over here, here we have x1 bar is 0 in this here. So everything's going to work the same. It was x2 bar if you're on the x1 axis. Well, so what if, say, x1 bar is 0? It seems that there is no epsilon such that the ball around x bar of radius epsilon is a subset of L. And that does independent of the norm. I mean, I'm using the max norm, so I get squares. But if I had used the Euclidean norm, I'd have circles. Same story, I'd have stuff sticking out. If I used the city block norm, for example, then I'd have a kind of a diamond. There'd still be stuff sticking out over here. So it seems like there's no epsilon, no matter how small I make it, that is going to give me a ball that is entirely a subset of L. But actually, let's say the ball around x bar of radius epsilon is defined, we defined it to be the set of all x in some set, the set that we're working in, and here the domain of U is not all of R. The domain of U is only R2 plus. We explicitly said in our interpretation of what's going on here, the consumer can't choose negative amounts of either x1 or x2, so the domain is simply the non-negative quadrant over here. That's the domain of U, and that's the domain in which we're going to have to work with our epsilon balls. So this is such that the norm of x minus x bar is less than epsilon, whatever norm we're working with. We happen to be working with the max norm, so this is going to be the max norm. And so in this case, what we say is we say that this this epsilon ball is open in R2 plus. Or we also say it's open relative to R2 plus. And in fact, that gives us a definition of an open set relative to some other set. So let's actually write that down as a definition. And it's going to look a little different than this to start with, but then we'll explain how it matches up with this. We're going to say a set S, subset of capital X, which itself is a subset of RL. That's what we want here. That's RL because I've used RL for the domain of our functions and the space in which the domain lives. So a set is open. Well, we know what it means to have the set open with respect to the overall space, but we want to say what it means for S to be open relative to the space that really matters for what we're doing, capital X, the domain of our function, for example. Although this definition works if we're using a set X for other reasons than the domain of a function. So a set is open in S or open relative to S if now this looks a little tricky here, so we're going to give an example in our example over here of how this works. If S is equal to some set, we'll call it S prime intersect S for some set S prime that is open in RL. Okay, so that might be a little obscure here, and actually let me underline these as I did up here because this is a definition. So we're defining the term open in S or open relative to S. It's a definition. So let's go over here and see how this plays out over here. So it says a set S, a subset of X here. So over here, what's going to play the role of X? So I'm going to put over here, what's playing the role of X? What's playing the role of X is R2 plus. Of course, what's playing the role of RL is R2, so I don't think we have to write that in maybe. And what's playing the role of S is the unit square. So that's going to be B X bar epsilon. And so what's playing the role of S prime? What's playing the role of S prime is this bigger square. And what's playing the role of S is this, and so I'm going to write over here that this, the part of the epsilon square that's in L, that is the epsilon square B of X bar epsilon intersect L, that's this. So this is S, or if you like, that's the set S, that's playing the role of S in this definition. And so you'll notice that S prime is a set that's open in R2, in all of R2. So S prime is a set that is open in all of R2, and S, or the set we're interested in, the ball around X bar of radius epsilon, which is just the shaded part, because it's just the part that's in R2 plus. So it doesn't look like the ball usually looks, because some of it's been cut off because it's not in L. It's not in R2 plus, more to the point, right? So this is playing the role of S over here, and indeed, the shaded part, as I already said a few moments ago, the shaded part, S, or this ball, is indeed the intersection of this open square in R2 with R2 plus, which is playing the role of X here. So this shaded region, which is the open ball, the epsilon ball about X bar in R2 plus, is open relative to R2 plus, open in R2 plus. And that's what it takes to be, for L to be an open set. It's got to be the case that there is an epsilon ball around each point that is a subset of L. And so here we've got a point, X bar, that's in L, and we actually have an epsilon, actually the same epsilon we found here. We have an epsilon such that the epsilon ball is indeed completely a subset of L, because the epsilon ball is just the shaded part here. I'm not going to write it down. It's in the lecture notes. We have the same definition for a set being closed in S, or closed relative to S. Let's see what else we should say here. I think we want to write down, this motivates actually, this example here actually motivates a further definition of continuity for real valued functions. So we already have 4 definitions of functions being continuous on a set X. And so here, X is R2 plus. We have the function U is continuous on R2 plus. We have those 4 definitions, so we're going to give actually some additional definitions that apply just to real valued functions. So let's actually do that here. So let's say that, and so the thing in the example that motivates this definition is this point right here, where I said that this set, L, the lower contour set, by the way, I used L because we think of this as the lower contour set with respect to theta. This lower contour set is the pre-image of simply an interval of R. Well, it turns out that if we actually, I think what we want to do here is maybe go back to the definitions we gave before. So I think we're going to take this off and we're going to put back on the screen our equivalent definitions. So we'll do that now. Okay, we got a little space back, and so what we're going to do here is put back on the screen all of the various definitions that we gave earlier. So I've kind of got the screen filled up with those over here, so I'm going to use this area over here to give a couple of more theorems, kind of like the theorems we have over here that are going to be characterization theorems for continuity. So I'll just use a different color here. Let's say we have first. Whoa, actually, I said definition here, but you know, I actually, these are going to be alternative definitions, but this is going to be a theorem, of course, that is going to tell us that the alternative definition is actually valid. Okay, so I should have written here theorem f from x into r. And so notice here that for this, for both of the theorems I'm going to write here, m is 1. That is, these are just about real valued functions. They don't work for functions where the target space is larger dimensional. So this, a real valued function, is continuous on x. We often leave out the on x because that's implicit here. X is the domain. A real valued function is continuous if and only if for every theta in R, it's the case that the set of all x in the domain such that f of x is less than theta and the set of all x in x such that f of x is larger than theta are both open sets. In x, relative to x. So notice that that's actually what was going on here. That here we took this set here is exactly this set here. It's the set of all, in fact, it's written the same way. Well, actually, let's just note that I didn't write it the same way, quite. Let's note that this is just f inverse, or the pre-image of minus infinity to a theta, and this is the pre-image of the interval from theta to infinity. So now you can see that indeed this is exactly what I wrote up here. And so notice that from our theorem down here, this alternative definition of continuity, it says that for any set that's open in Rm, so that would be any set that's open in the set of reals here, because this is the target space. Any set that's open in the target space, the pre-image has to be open in the domain. And so one implication of that would certainly be that for any theta like this set, of course, is the pre-image of an open set in the target space, so that has to be open. This is the pre-image of an open set in the target space, so that has to be open. So certainly the fact that both of these are open is a consequence of f being continuous according to this theorem. But the theorem here, the strength of this theorem is that it goes the other direction. It says we don't have to prove for a real valued function, we don't have to prove that the pre-image of every open set in the target space is open. We only have to prove that the pre-image of this set and this set is open. The two printed images are open, of course, for every theta. And that's what we did. We didn't prove it for the upper contour sets, but we proved exactly that the pre-image of this set here is an open set for any theta. So we exactly proved this part right here, and it's clear we could have done the same exact thing over here, and then we wouldn't have to worry about this business with the axes and so on. We could have done exactly what we did by just reversing the inequality on our utility function being less than theta. We just change it to being greater than theta and then do just what we did. So we actually proved, given this theorem, we proved that this utility function is continuous according to this theorem. And so let's say one other thing, and that is that yet another theorem, yet another equivalent definition is if I make these inequalities weak inequalities and change this to closed sets, then that theorem works too. So that's another theorem. I'm not going to write it all out, but that is that f is continuous on X if and only if the pre-image of that set and that set are closed sets in X. One more theorem, then we'll be done. Real valued function is continuous on capital X if and only if for every point in the domain, capital X, it is the case that, in fact, let's make that an X bar. I don't want it to be confused with the X bar up here. But let's just write these sets. So this is the set of, I better do it this. This is the set of all X in X such that f of X is less than f of X bar. And the set of all X in the domain such that f of X is greater than f of X bar. Are both open sets in the domain. And you can see that as soon as I have one of these theorems, I have the other. It's just a triviality to take this theorem and use it to convert it into this theorem here by making the theta equal to the f of X bar, or the f of X bar equal to the theta. And of course that means that this theorem would also hold if I change it here and I change this to close. So we have a plenitude of equivalent alternative definitions of continuity of a function on a set, especially if we're talking about real valued functions like this, because then we get these additional things. And notice that this, again, I want to emphasize, this is exactly what we did over here. And this is exactly the way you're going to be doing things with utility functions and their continuity properties in the first microeconomics course in your fall semester of the program. Probably this theorem, or one of these two theorems, which they're basically the same theorem, one of these two theorems is what you will use to analyze and work with utility functions and their continuity properties. So I think that really pretty much covers the waterfront, I think, for everything we want to do with continuous functions. So that's it for today, and we'll see you all next time.